Hello everyone, and welcome back to this Chemical Engineering Economics and Project Management class. So in this second segment in first module, we will discuss about how a process plant project is being developed from the start to the end. So project in the chemical process industry varies widely in terms of scope and complexity. For example, it can be as simple as routine maintenance and incidental repairs of equipment. It could be the development and implementation of new products, process plant debottlenecking and revamping. I hope you are familiar with these two terms. Okay, if not, I urge you to look it up in the internet what those two terms mean. Okay, and this is perhaps one of the most complex projects that a chemical engineer can encounter, which is a turnkey process plant development, which means process plant development literally from zero, from scratch. And this complexity of process project is determined by various factors. For example, the production capacity of the plant, technological level involved in the plant, geographical factors such as what you see on the right hand side here. This is the Abadi LNG project, okay, Abadi Masela gas field, which I'm sure you have read in the media, that the geographical challenges of this project is actually quite enormous. This is a project developmental phase for very complex projects. So in real life, actually, not all projects has to go through all of these steps. It really, again, depends on the project complexity. If you have a very simple project, then you don't have to go through all of these 6 steps. But so this is the most complete scenario for complex projects. Okay, and those developmental stages are: one is feasibility study. And again, this is not exact science, so some people or some organizations, some reference might have different terms, and this is really dependent on the organization doing the development and such, and so on and so forth. Typically, a feasibility study can involve preliminary FS, the FS itself, and also bankable FS. Okay. And then from the feasibility study stage, we go through front-end engineering design, abbreviated as FEED, F-E-E-D. Okay, and it's also called as front-end loading, or FEL. And FEL, again, is split up into 3 different sub-stages, so to speak: FEL 1, 2, and 3. Okay, and step number 3 is detailed engineering design, or DED. Steps number 1 to number 3 is also frequently called or classified as quote-unquote engineering projects. Okay, so when chemical engineers say, oh, this is an engineering project, and so they will refer to these steps. Okay, and then going to the next step is procurement, meaning we purchase the equipment to build the chemical processing plant that we want to build. Construction, as the name implies, it's quite clear, so this is the step where we build the plant. And then lastly, inspection, commissioning, and startup. Okay, and these last 4 steps are collectively they're called EPCC: engineering, procurement, construction, and commissioning. Now, I will not go through a lot of detail in this graph. This simply tells you that a project life cycle is actually quite involved, starting from the initiation of the project, conceptual design. If the initiation step produces in a promising production concept, then it can go then it can move up to feasibility study step. Okay, and then if it is still deemed prospective, then it goes to the next step, which is front-end engineering design, and so on. An important thing to remember here is that between each steps there has to be an appraisal, there has to be an evaluation of whether we should move forward, or we cancel it, or we move to another direction perhaps. Okay, so going from first step to the next one, and the next one after that requires appraisal or evaluation of feasibility. Okay, so thereby going from top to the bottom here, the design of the project of the process plan gets more and more defined. Okay, and this is a typical behavior of projects, not just chemical processing plant, but almost all engineering projects behave like this. This is an investment profile plotted against time. So this would be T equals 0. So this is the initiation of the project. Initially, typically project will consume little money. Okay, especially if you're still in the early design stage or conceptualization stage, then it is, it doesn't require much funding to move forward. But at some point when we start to build the plan, see, this is the EPC stage. When we start to build the plan, then we will see that the cost will increase rapidly. Okay, so this is the reason why this is negative, because this plot tells you the cash position of the project. Okay, so negative means the project is still burning money, it's still losing money, it's not profitable yet. And then this is the operation phase. Then you see that the curve starts to go up, which means that the project starts to generate money, to generate income and profit to the company. And then at some after a certain period of time, hopefully that we have a net profit from the project. Okay, so we're going from negative to positive cash position. And on the right hand side here, this qualitative graph tells you what the opportunity to improve design. Okay, so at the early stage of a process, it's very easy to change. Okay, so imagine when you're doing your plant design project, okay, your tugas air rancangan pabrik, we call that a basic design or preliminary design. Okay, in which it's very easy, it's very cheap to change the design while it is on the conceptual stage. However, when you start to purchase the equipment, the main equipment for the plant, then it gets much more expensive to make any changes to your design. In fact, hopefully you're not making any substantial change in the design when you start to procure equipment for your plant, right? This all makes sense. Okay. However, after some time, and this is assuming that your everything goes well and your process plant starts to operate properly, and then at some point in its life, opportunity will present itself where we can improve existing plants. Okay, so that's what's going on here. Okay, so as the plant ages, actually you have to start to think, okay, so what can we do to modify this plant? What can we do to improve its energy efficiency, to make it to keep it competitive, right? So that's what's going on here. Now let's do a quick review about each of those design stages. Okay, so the first one is FEED, or front-end engineering design. Front-end refers to the initial stages of plant development, where it is very much possible to make changes even to the basic design of the project. Okay, changing the PFD is still very easy at this point. Okay, and if necessary, FEL or FEED can be defined further into several stages and integrated with funding feasibility review to move to the next stage. Again, as I told you just a few minutes ago, whenever we move from one design stage or one project stage to the next one, there has to be what is called a stage gate review. There has to be a review done properly to decide whether we should move forward or not. The design information package produced by FEL is known as the process package. Okay. Briefly speaking, a process package is a process design that does not contain any location-specific details. Okay, so expected output for FEL1 is mass and energy balance, project charter. You will learn in the last module of this class what a project charter means. FEL2 will produce preliminary design of equipment, plant layout, and so on and so forth, project master schedule, preliminary cost estimates, and then moving forward to FEL3, we have final specs of main process equipment, definitive cost estimates, and so on. Okay. And as a side note, in Indonesia, AMDAL, or Environmental Impact Analysis, is sometimes run in parallel with FEL2 or 3. Okay, so this is the typical content of a FEED: mechanical data sheets of main equipment, thermal rating calculation for heat exchangers, preparation of bid document packages, development of PNID, and so on. Okay, I urge you to read more about these outputs of FEED project. Okay, all right, and then moving on to the next stage, detailed engineering design. Okay, this is actually, even though this is the next step from FEED, actually it's a very long jump. It's a very high risk jump going from FEED to DED. Okay, because there's a lot more detail involved in a DED compared to FEED. Okay, so Essentially, DED elaborates the process package. Remember, process package does not yet contain any location-specific or condition-specific design information. It has to be adapted to the project location, to the project circumstances, okay, into a ready-to-build detailed design package. Okay, ready-to-build means it has already been adjusted to local conditions with as much detail as possible. Local conditions include something as simple as where do you want to build the plant, okay? What is the land topography look like in that location, okay? Do you have to watch for example, local settlements, where you want to put your piers, your loading station, your offset facility, and things like that. So those would be site-specific design information, okay? All right, and there's a lot more detailed information that is produced by DED. Okay, again, please read this by yourself. It will take too much time if we review it one by one. Okay, however, I do have some example of these documents. Now, what I want to show you, what I want to impress upon you is the complexity, the sheer complexity of a DED compared to FEED. Okay, so the first one, of course, you need to produce a complete set of piping and instrumentation diagram, PNIDs. Okay, so this is not the simplified PNID like you do on your rancangan pabrik, but this is the real thing. Okay, this is the complete PNID, meaning all lines have to have its code. Okay, all control valves. Okay, and its ancillaries has to be labeled and things like that. So this is a very involved document. Okay, it's a very complicated document, and you have to do this for all of your processing units. Isometric drawing. So you also need to lay out your piping, okay, and you have to start to consider the 3D aspect of your plant design. Okay, equipment A is connected to equipment B. What level? What is the elevation of flange, the outlet flange from equipment A going to inlet flange for equipment B? Do you have to route the pipe to avoid, for example, manways and things like that? So again, this is a very complicated mechanical engineering work here. Okay, now MTO, or material takeoff, is essentially a shopping list. Okay, shopping list for your piping especially. Okay, so this would be the line number or nomor pipa. Okay, and these are all each and every fittings, each and every accessory that is included within each line. Okay, how many valves, how many fittings, how many elbows, everything. Okay, everything has to be accounted for to make an MTO, materials takeoff. Again, there is a shopping list to build your chemical processing plant. And this one again, please do kindly read it on your own. This is just another other version of how to define engineering developmental stages. This one, this nomenclature is prepared by Technip, which is it's a engineering company from France. Sometimes each engineering company or people or reference have their own terms, so you should be. It's good for you if you're familiar with the terms used in these engineering companies. Okay, there's basic engineering design, for example, okay, and so on and so forth. In Technip's term, a basic engineering design includes conceptual process design. Okay, this is what you do in your rancangan pabrik. Preliminary PNID, types and sizing of our capacity of main equipment, and so on and so forth. Process effluent specification, basic design of control loop, okay, also required in your rancangan pabrik, right? So BED, or basic engineering design, can lead to the preparation of process package based on process license from external licensors. So of course, if you want to do this, you will need collaboration between process licensor. So these would be companies that own the license, and engineering companies that is charged with building the plant. Okay, so collaboration between these two sides will result in process package. Now, just a quick example. This is a picture of plant number 4 in Pupuk Kaltim. Yeah, this is taken from their website. Right? And if you take a look at the words that I put in box here, okay, so this plant uses the Haldor-Topsy process for the ammonia and Snapper-Getty process for urea plant. So these two companies would be the process licensors for Pupuk Kaltim 4. And it's not written here, but if you browse it in the internet, you'll find that the engineering main contractor for Pupuk Kaltim 4 was PT Rekayasa Industri. Okay, so there the Rekayasa Industri was the engineering contractor, and these companies are the process licensors who sold their license to Rekayasa Industri. Okay. All right, and this is just a quick example of the difference between plot plan and plant layout. Plot plan gives you a rough idea of the area designation of your entire plant or entire facility, including inside period limit and outside period limits, or we also call it offsite facilities. Okay, so not only we have the main process area, but you can also see here we have this auxiliary buildings, warehouses, administrative building, control rooms, and things like that. You can also see where the fuel tanks are located, okay, for the plant. The gate, so this would be the layout of the gate of the plant, right? However, a plant layout will give you a more detailed view of where the individual equipments are placed. Okay, so these small boxes represent process equipment, okay, drawn to scale, and this would be the pipe rack. This is the main highway, so to speak, okay, for the piping to go through. So this table gives you the classification of cost estimates based on AACE, American Association of Cost Engineers. Okay, and each of these classes are appropriate for a specific project development phase. Okay, so some of these classes, so larger number meaning rougher estimates, right? So class 5, for example, is suitable only for FS or feasibility study. Class 4 may be used for FS. It can also be used for FEED, at least for FEL1, for example, and so on. And this is the end usage of the cost estimate and the methodology of cost estimate. We will discuss this in much greater detail in the next chapter. Okay. Okay, so this is the end of segment 1.2, and we will meet again in the next segment. Thank you very much.